Hello and welcome to this exciting tutorial on relative humidity. We often check weather updates, which show parameters like temperature, wind speed, and a humidity percentage. That percentage is actually relative humidity, an indirect measure of water vapor in the air. Other metrics, like vapor pressure and dew point, also indicate moisture levels. I've covered vapor pressure in a previous video, link in the description, and dew point will be explained in an upcoming one, so don't forget to subscribe to the channel for updates. In this video, we'll focus on relative humidity. By the end of this video, you'll be able to define relative humidity, solve related examples, and understand the factors that affect it. We will also explore why air cannot be saturated beyond 100% and why higher relative humidity doesn't always mean more water vapor in the air. So, without delay, let's dive in. Relative humidity is the ratio of the actual water vapor in the air to the amount needed for saturation. The air is said to be saturated if the rate of evaporation equals to that of condensation. A few key points need to be noted for relative humidity. It is expressed as a percentage, it shows how close the air is to saturation, and it doesn't directly measure the water vapor content. Using the definition, we can express relative humidity mathematically. It is also written as the ratio of the mixing ratio to the saturation mixing ratio. The mixing ratio is the amount of water vapor per kilogram of dry air, and the saturation mixing ratio shows the maximum water vapor air can hold at a given temperature. Let's take a closer look at its temperature variation. Here is the table showing how the saturation mixing ratio changes with temperature. The first column lists the temperature in both Celsius and Fahrenheit, while the second gives the corresponding saturation mixing ratio. So, for any given temperature, you can easily find the saturation mixing ratio. Notice that as temperature rises, so does the saturation mixing ratio. Now, let's calculate the relative humidity of 1 kilogram of air at 25 degrees Celsius containing 10 grams of water vapor. So, the mixing ratio is given to be 10 grams, and from the table, we see that the saturation mixing ratio at 25 degrees Celsius is 20 grams per kilogram. Plugging these values into the formula of relative humidity, we find that the relative humidity is 50%. Now that we have solved an example, let's move on to the factors that can affect relative humidity. Let's revisit the mathematical definition of relative humidity. The numerator represents the actual water vapor in the air, and the denominator is the saturation mixing ratio, which depends on temperature. So, if we add or remove water vapor, we are changing the numerator, while changing the temperature alters the denominator. So, let's think about what happens to relative humidity when we change the water vapor content without changing the temperature. Imagine we have a beaker filled with 1 kilogram of air and some water at 25 degrees Celsius. The air inside the beaker contains 5 grams of water vapor. Now, we want to find out the relative humidity. Here's the scoop. According to our handy table, the saturation mixing ratio at 25 degrees Celsius is 20 grams per kilogram. Since we have 5 grams of water vapor in 1 kilogram of air, the relative humidity turns out to be 25%. This means the air is quite dry, only a quarter of its vapor holding potential is being used. As a result, some of the water will evaporate into the air to increase the vapor content. Let's fast forward a bit. Suppose, after some time, the water vapor content in the air rises to 10 grams per kilogram. Now, the relative humidity is 50%. The air is still not fully saturated, so evaporation continues, adding more vapor. Eventually, if the water vapor content reaches 20 grams per kilogram, the relative humidity hits 100%, and the air becomes saturated. The key takeaway is that adding water vapor to the air at a constant temperature will increase the relative humidity, while removing water vapor will decrease it. Now that we have covered how changes in water vapor content affect relative humidity, let's explore how changes in temperature influence it. Let's dive back into our beaker experiment. The air holds 7 grams of water vapor. According to our handy table, the saturation mixing ratio at this temperature is 14 grams per kilogram, so our relative humidity is 50%. Now, let's cool things down to 10 degrees Celsius. At this lower temperature, the saturation mixing ratio drops to 7 grams per kilogram, and the relative humidity rises to 100%. This shows that as the temperature decreases, relative humidity increases until it reaches saturation. But what happens if we cool the beaker even more, to 0 degrees Celsius? The saturation mixing ratio drops to 3.5 grams per kilogram. You might wonder if the relative humidity could exceed 100%, but it doesn't. Instead, what happens is a bit of a condensation party. At 0 degrees Celsius, only 3.5 grams of water vapor can stay in the air. So, the excess water vapor, an additional 3.5 grams, condenses into liquid water. The air remains saturated with a relative humidity of 100%. Essentially, as we cool the beaker, the excess vapor condenses out until the air is just right, maintaining that perfect 100% humidity. Here's a crucial question to consider. Does higher relative humidity always mean there's more water vapor in the air? You might think so, but that's not always the case. The key lies in understanding the saturation mixing ratio, which changes with temperature. For example, air can have a high relative humidity even if the actual amount of water vapor isn't that high, thanks to lower temperatures reducing the saturation mixing ratio. Let's wrap up our discussion on relative humidity by highlighting the key takeaways. Thank you so much for tuning in, and I look forward to seeing you in the next video.